The first problem on the exam was a straightforward one that we did in class, and you had at least one, I think 2 homework problems related to this. So you had A here, and it had a probability of working of 0.2. Then you had B, and it had a probability of working of 0.4. Correct me if I'm wrong on this. And then you had C, and it had a probability of working of 0.4. Then you had D, and I think this one is 0.6. Comes down, and then you had E, and it's 0.6. And then you had F here, and the probability of working is 0.5. And this is the sender, and this is the receiver. So part A was, I want the probability of this actually working if F working. We're going to need them both, but for F working, so I'm going to redraw it. And this looks like 0.2, 0.4. This is the probability it's working. 0.4, 0.6, 0.6. And here's the diagram you're dealing with. Oh, it's working. Sorry. It is working. So this is just a short, right? From here, if I draw it, a redraw, I have 0.2. Then I have these 2 legs in parallel, 0.4 and 0.4. Then it's connected, or sorry, 0.6, my bad. And then I have another one, 0.4 and 0.6. And then this. And I think everybody agrees. All right, now I'm going to show, if I look at just this segment right here, I have probability of this working is 0.4. Probability of this working is 0.6. Now I look at probability of it not working, both of them not working. So that's 1 minus that and 1 minus that. So the probability of this system not working would be probability of that times probability of that. If you look at this, this is going to be what? 0.6, and this is 0.4, right? And that's the probability of it not working. So 1 minus that is the probability of it working. And what I'm going to do is replace this section. This is the probability of what? It not working. This is the probability of not working. The probability of this not working is this times this, right? 1 minus that is the probability of working. It's that 1 minus 0.4, 1 minus 0.6 multiplied together is the probability of this. All right, now 1 minus that is the probability of it working. So I'm going to just put that right here. 1 minus 0.6, 0.4. I know we can multiply that. And that's the probability of this link working. Now there's another link identical to it. So I'm going to just square that. This is the probability of working. Now they're in series. And the solutions are up there so I can look. The probability of this working is going to be 0.2 times 0.2 times the quantity 1 minus 0.6, 0.4 quantity squared. I forgot what that was, 0.116, but that would be the probability of working for part A. B is C is not working. If C is not working, I'm going to do the redraw. For that one, you have 0.2, then you have 0.4, then you have, this is probability of working, 0.6, and then you have 0.5, and then you have 0.6, and these are all probability of working. And I'm trying to find out what the probability is of the sender and receipt of this system working. Now it's reconfigured. This kind of stuff is going to appear on the final. I would write that down. This kind of a problem is going to appear on the final because there were a lot of people that frankly didn't know what to do with parallel and series, and I was a little concerned about that. The first thing I'm going to do is multiply these 2 together because they're in series and replace it with a single link. So this is 0.4 times 0.5, and so that's what? It's going to be like this. I'm trying to show these in parallel. 0.4 times 0.5, so it's 0.2, and it's in parallel with 0.6 as such. And then there's going to be a 0.6 here. Now, this is just 0.2, right? So now I'm going to do the same thing I did before, only with different numbers. Same identical format. So the probability of the top one not working, and I'll leave it in this form, would be 1 minus 0.2. Of the bottom one not working is 1 minus 0.6. All right, now the probability of this whole thing not working would be 1 minus 0.2, that's 0.8, and 1 minus 0.6.4. So that's the probability, I'm sorry, this is the probability of the whole system not working. 1 minus that would be the probability of it working. And what is that? 1 minus, this is 0.8 times 0.4, right? And I'll leave it like that. I'll redraw this. So I have 0.2, and then I have a series length from here to here of 1 minus 0.8, 0.4 probability of working. And then I have 0.6. So the whole thing, the probability of this system working is going to be 0.2 times 1 minus 0.8 times 0.4, 0.32, and then it's times 0.6. And what's that value? 0.0816. C and D not working. If C and D are not working, the path would be here, 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 and here. You agree? I'll redraw it. So I have this, goes to here, 0.2. This is 0.4. This is 0.5. And finally, this is 0.6. And this one is just multiplying them all together. So that means the probability for C working is 0.2, 0.4, 0.5, and 0.6. And what's the answer for that? 0.024. D, probability of system working. What we really know is the key is this middle section, right? So first, we leave the middle section in, and we find the probability if F is working, and then we find the probability of it working if F isn't working. So the probability of it working is part A, I believe. So probability of working, or probability of, I'll call it F working, is what?
No, 0.1155.
Now the probability of F not working,
We don't know.
we're going to get it.
Yeah.
So if it's not working, now I can go right here and do this one. We know F is 0.5. If it's not working, it's this, correct?
Mm-hmm.
All right, now I'm going to simplify this. That's 0.4 times 0.4 there. That's 0.4 squared. Do you agree with that?
Yeah.
And then we find the probability of it working if F isn't working. Of it working. So I'm going to just do that. So this whole top leg can be replaced by 1 and 0.4 squared. Likewise, the bottom one can be replaced 0.6 squared of it working. Now, 1 minus that is the probability of that one not working, and 1 minus that is the probability of that one not working. So the probability of this working would be 1 minus, and then it would be 1 minus 0.4 squared times 1 minus 0.6 squared. I have to multiply that by 0.2 to get the probability of the whole system working. So I take that whole thing and I just multiply it by 0.2, and that would be the probability of this system working in that configuration, like 0.925. All right, now probability of the system working is going to be 1/2 times 0.1155, I think. I'll just put 116 plus 1/2 times 0.095, 925. What is that? 0.104. So it's a Rayleigh distribution of current, and they give the mean value of the Rayleigh current to be 2 amps, and the resistor's value is 4 pi. In the book, it was 2 pi. All right, for this one, I give you the mean value of a Rayleigh distribution is equal to, and this is the square root of 2 over pi, right? Times sigma, that's the Gaussian sigma. Didn't I put that on there?
You did.
All right, so for that one, I know the Rayleigh current, the mean value is 2, so I can say sigma, and you might want to put sigma Gaussian down here if you want to, is going to be 2 times root of 2 over pi. That's important that you have that sigma value. What was the first question?
Mean value of the power dissipated. EP.
The mean value of the power dissipated is going to be the expected value of R times I squared, right? And so that's really R times the expected value of I squared. For this one, remember that for the Rayleigh distribution, the expected value of I squared is 2 sigma squared. If I want this right here, the expected value of power, that's 4 pi, right? It's times 2 sigma squared times 2, and sigma squared is going to be what? 4 times 2 over pi, right? And so the pi's cancel. What do you get for that? 64. Oh, what's the second part?
Probability that the power is less than or equal to 24 watts.
This is part B. Probability. And now we want power. Power less than or equal to 24 watts. So power is equal to I squared R. So now if I take power over resistance and I take square root, this is the value of I that will be the threshold value. So that's the square root of 24 over 4 pi.
1.382.
So the probability it's less than this is Rayleigh then. So f of I, large f of I for this, is 1 minus exp. This was the probability it's less than or equal to this value of I squared over 2 sigma squared. So that's 1 minus exp. Now I'm just putting up what everybody should know, that the Rayleigh distribution, right? And this is the cumulative distribution, so it's exp of I squared, and that's going to be 1.382 over 2, and then sigma squared is, so that's going to be 4 times 2, 8 over pi, isn't it? Yeah, 8 over pi. Thank you. And what do you get for that? 0.3127. Everybody agree with that? What's part C?
Probability that its power is dissipated greater than 72.
All right, now we want this. We want the probability of the power greater than 72 watts. And here again, you go to this equation. So power is equal to I squared R is equal to 72. 72 over 4 pi is equal to I squared. I is equal to the square root of 72 over 4 pi. Now this is just the threshold. We need to find this value of I. We're going to be above it. What's this going to be? 2.39? Okay. Now, you know this f of I that I had up there is the probability from 0 to that point I, right? So I'm going to just say this. F of I is really the probability that really the value of I is equal to or less than this value, and that's 1 minus exp minus I squared over 2 sigma squared. Well, the probability if it's greater than that is 1 minus this. It's just the exponential, right? So the probability that I is greater than the value of 2.39 is just equal to exp minus 2.39 squared over 2 times sigma squared, which is going to be 4 times 2 is 8 over pi. There's my answer. So what is that? 0.325? You're going to see something like this in the final, but don't quote me as that exact kind of problem. Something like this. You with me, class? And it might be something where you got, you know, dart thrown at a board, or something where you got an actual circular target. So this is problem 3.
F of x equals 2x between 0 and 1.
0 greater than x less than 1. And 0 else. Right? This is the problem, the classic problem. And then we have what?
Y is unit greater than -1.
Fy of y is just, since it's from -1 to +1, uniformly distributed. So it's between -1 and 1, right? Right. F of y is just 1/2 -1 to 1. Then they said we got a variable, right? And that's z. And z equals x plus 3y.
Yes.
And the secret was just create a new function, right? I mean, you didn't have to, but it makes life easier. I'm going to say that really z is equal to x plus g, and g is 3y. So now I need the density function, and this one's going to be from -3 to 3, and it has to have a value of 1/6, and this is my f of g. So when I do this,
You got to say with 1/6 again for real quick again.
you look at this, what's the span on this? If the span of y is from -1 to 1, right?
Okay.
The span of G is from -3 to 3.
Okay.
All right, the height has to be constant. The only way you get an area of 1 is if the height is 1/6. That's my. This is the classic problem of convolution. And we could write it in terms of an integral. To do that, we could say f of z would be equal to an integral. And here we could have f of x, and this would be of x, right? And then times f of g, and it would be z minus x, right? And it would be dx integral. And technically it's from -infinity to infinity. This is the definition of convolution, isn't it? If I replaced the dummy variable x that's going to be integrated out with tau, it would be fx of tau times fg of z, or any constant, minus tau d tau. That's the convolution integral. So if we're doing convolution, now if they were both exponential functions that started at the origin at 0, then what I would do is just the Laplace transforms of both and multiply. But because this little boxcar right here, in order to do this, you don't use pulse functions that much, but this could be defined as a pulse function. The pulse function would be 1/6 times RECT of, and the variable here, it doesn't matter. You can call it x, it doesn't matter because you're going to integrate that part out. And it would be 1/6, and then it would be the pulse function, RECT of x over 6, because 6 is the width. Do you all remember that? It's centered at the origin. You could do that, and then you could take, it would have to be Fourier in this case, Fourier transform of that times the Fourier transform of the exponential, multiply them together, and then do a partial fraction expansion, a pole expansion on that one, if you wanted to. But you're not that familiar with that for boxcar function. I know that. So what I'm going to do is just say, we'll do the convolution, right? And if we do the convolution, I'm going to not shift the f of x right here. F of x is just linear, so I'm going to leave it alone. And we'll integrate out x, so I'll even use x down here. So here we have x, and this is 1, and this is f of x. And it's equal to 2x in this range, 0 outside. Then down here we start with a boxcar and we shift it. The boxcar has a width of 6. So this is going to be, if you look at this, this starts at 3, so it's going to be z plus 3 here, and this is z minus 3 here. You have to flip and shift it. The boxcar is going to move through here. It has a height of 1/6. Before I continue, I want to talk about the regions, and then we'll do each one. Now you can see, if this is the actual width of this, when it's moving that way, here's the region of overlap in the beginning. And that's from -3. From -3, z equals -3, we put at this point right at 0. And it would be from -3 to when it gets all the way through here and hits 1 would be z equals -2. And I put down for z greater than -3, less than -2, I get my f of z here equal to, and it's going to be this function. You can integrate x. It's going to be from 0, and this is 2x, right, dx, and the upper limit is z plus 3. And there's going to be a 1/6 here too, because that's the weight on the curve. It's the height of the curve.
And you're going from 0 to z plus 3 because that's what you have. It's
It
bound to
starts at
x.
0.
Yeah.
All right, there's the function here is 0, so you don't care.
Yeah.
You start at 0 and you go to the point where it stops.
Which is x equals 1 or
No, no.
z.
Yeah, anywhere in here, but it's valid from -3 to -2.
Oh, yeah, I see. Okay.
All right, so this is going to be 1/6. Now when we integrate x dx, you get x squared over 2, there's a 2, it becomes x squared from 0 to x, z plus 3 is just z plus 3 squared. And that's fine. I mean, from -3 greater than z, less than -2. Now, z's past -2, right? This is z plus 3, z minus 2. Now z is greater than -2, right? That means this part is past 1. And how long is that going to go on? Well, until the back end of the boxcar starts coming through, right? And that's going to be from what? Total width of this is going to be what? The sum. So it's going to be 6 plus 1 is 7, right? We already went 1 away, so it's going to be from -2 to 3. You look at this from z equals -2, greater than z, less than 3. You agree with that? Let's see. When z is equal to 3, this is 0. Do you agree? That's when this thing starts pulling on through, and then we have to worry about a different regime. But all through here, it's just this area times 1/6, this height. Do you agree with that, everyone?
Because all of that function fg is in fx.
If you look at the multiplied, if you take this times this, the multiplied area, and do the integration, it's just this area times 1/6. That area is exactly 1. 1 times 1/6 is going to be 1/6. So it's just equal to 1/6. Once the curtain is completely covering the f of x function, you might say, it's the area of f of x times the height of the curtain. That's all it is. All right, next part. Now you go from 3 greater than z less than 4. Now if you look at this, now this part is past the 0 point, but you're still integrating up to the point 1. So here, I know my f of z is going to have a height of 1/6, right? And the lower limit is now z, right there, minus 3. The upper limit is 1. It's still 2x dx. And if you want to put 2 tau d tau, that's fine. This is a dummy variable. It isn't going to be at the end. What happens to this? Well, it's the same as this one here, just the limits are different. So it's 1/6. And then you're going to get x squared over 2 times 2, or x squared evaluate these limits. And you get 1 minus the quantity z minus 3 squared. And that's what it is from, do you all agree with this? Now you can square the thing out, and you can go ahead and take care of the 1 and the 9, because you're going to get minus 3 squared is going to be what? That's going to be 9, then you get 1 minus 9 is minus 8, and you can get that, you get a minus z squared, right? And you're going to get, 6z in front, but you can do it. And what it looks like, we know the span, it goes to 4, right? Starts at minus 3. First, check yourself. These are 2 finite duration functions. If they're convolved, the total width has to be the sum of the 2 widths. That is a width of 1, this is a width of 6. Our total span should be 7 down here, and it is. So it checks that box. So from minus 3 to minus 2, the function is 1/6z plus 3 cubed, right? So it does this. 1/6z plus 3 cubed here. Or squared, sorry, squared, my bad. My bad, right? Then it's constant, 1/6, right? All the way up to 3, right? All the way up to 3. 1, 2, 3. And then it goes down at 1/6. It basically is doing this. 1/6, 1 minus z minus 3 squared. Now we have f of z. And now that's the probability for it being from minus 3 to 0. All right, so the probability of z being greater than minus 3 and less than 0. That would be equal to the integral from minus 3 to minus 2 of f of z, which is 1/6z plus 3 squared dz plus, and then it's going to be 1/6. Follow me. I want it to 0, right? The probability z is less than 0. This is a density function. So I integrate from here to here, and then I integrate from here to here. Well, integrating from here to here is just the height, 1/6 times the width, which is 2. Or 1/3. I'll put that down. It's going to be plus 1/6 times 2. Now this integral, that's just going to be in the form of x squared, and I'll show you what I mean. I'm going to call a new variable, call it x. I'm going to let x here be equal to z plus 3, and that means dx is equal to dz. All right, so now I can say this is equal to an integral of 1/6 x squared dx, but the limits will change. If z is equal to minus 3, x is equal to 0. If z is equal to minus 2, right here, x would be equal to, so it's that plus really 1/3. And you can see this is going to be 1/6 here. Then when I integrate x squared dx, I get x cubed over 3 from 0 to 1 is going to be 1/3 plus 1/3. And what is that? That's 1/3 times 1 plus 1/6. And I don't know what that is, but what is it? That's going to be 7/18. Now listen, if I asked you the probability of z being between 0 and 3, this should be a gift if you've got the density. You all follow me? It's just 1/6 times 3. The tricky thing would be the mean value of z, because then you would have to take z times this to the integral, plus then you have to integrate z times 1/6 from here to here, plus z times, you follow me? That takes some time. That I'm not going to ask you, but I just want to tell you, what you're up against if you're doing that. All right, last problem is what?
Such an independent random variables x and y.
All right, now wait, x, y, important is independent. That means the correlation coefficient is 0 for those two. That's very important.
Sigma squared x is 36.
Sigma x squared is 36, and sigma y squared is 9. All right, let me do one other thing. Sigma x is 6, sigma y is 3. Go ahead.
And v equals 5x minus 2y.
Mine's 2y. So the first thing I asked for is what?
Find the variance of u and v.
Sigma u, right? Well, here, because rho of xy is 0, right? Here's u, right? So this is going to be 9 sigma x squared, right? Plus 16 sigma y squared. I'm squaring the coefficients here. Then it's going to be plus or minus. In this case, it's plus 2 times rho, and this would be xy times mean value of x, mean value of y. Oh, I'm sorry.
Times
Oh,
A.
sigma x, sigma, you're right. What?
And it'll be A times B at the end.
Yeah, it's times 9 times 16, but it doesn't matter why.
Because
Rho x,
Zero.
rho xy is 0. So I guess I'm not even focused on that. I know it's going away. So that's 468. Now for sigma v, all right, now I gotta take 5 squared, or 25, times sigma x squared, plus 4 times sigma y squared. And again, this part goes away because the rho of xy is 0. Now if it wasn't, you'd have to include it. And what is this?
936.
Now, so I want rho of VU, right? And in the book, he's going to have this. This is all over. Sigma V times sigma U, right? Whatever these variables are have to be here for the standard deviation. And then up top, it's the expected value of U times V, right? Minus U bar V bar, right? Now let's just plug and chug. Rho VU equals the expected value of UV is the expected value of U. So it's 3x plus 4y times the expected value of V, which is 5x minus 2y. I gotta multiply these out. That's gonna be minus U bar V bar over sigma V, sigma U. This is the one you gotta be careful about. If I look at the expected value of 3x plus 4y times 5x minus 2y, I'm going to go ahead and square those things out. So I get 15x squared, that's going to be minus 8y squared. I got products here, so I'm going to have plus 5 times 4 is 20, and minus 2 times 3 is minus 6, and it would be xy. And what I need is the expected value of this. Y'all agree with that? I'm trying to break this down so I can take that and put it up there in the next step down over here. When I go ahead and do this, this is the expected value of, really what I'm going to do is break this down. When I look at this 15x squared can be replaced by sigma x squared plus x bar squared. So I'm going to just do that. I have 15 here, and I'm going to have sigma x squared plus x bar squared minus 8. And here you're going to have sigma y squared plus y bar squared. And you're going to have plus, that's going to be 14. But since these are independent, it's the expected value of x times the expected value of y. I hope you all follow me. Now that's just this part, the expected value of uv. I'll subtract minus, and but the mean value of u is just going to be 3 times x bar plus 4 times y bar times the mean value of v is 5 times x bar minus 2 times y bar. And all this right here is divided by sigma v, sigma u, my bad. And this is rho uv. First, you all agree with me? I'm going to put this sigma v, sigma u down as a square root of the 2, so the square root of 36 times 9, because that would be the square root of either, right? You agree with this, everyone? Now when you do this, one thing I think most of you see when you end up with this, all the mean values of x and y cancel. I mean, we can do this, but if you just take a look at this, you see how you get 3 times 5 is going to be 15 x bar squared. Do you see that? All right, there's a 15 x bar squared here. They cancel. See that? Then for y squared, I get a 4 times 2 is 8 with a minus sign. It's minus 8 y bar squared. Follow me? There's going to be a minus 8 y bar squared here. Everything cancels with the mean values here, right? So what's left? You're going to get 15 times sigma x squared minus 8 times sigma y squared over the square root of 36 times 9. And I want to say that's 0.707, or 1 over square root of 2. That's 1 over the square root of 2. And it was meant to be just a template problem. I'm probably going to scale, but it's not going to be add this many points to your thing. There's going to be a multiplying factor where you take your score and you're going to multiply by that factor, and that will be your grade. Now, the reason I'm saying that, I think the average was like 60. My plans now, from here to the end of the semester, we are going to finish up Chapter 3. We're going to do autocorrelations, spectral density, and I'll map it out. I'm going to give you some reading and some homework to try. And I'm going to do this next time because this is Friday. On Monday, I want you to please put some time into it.